Good morning, class. So today we're going to finish up our discussion of bipolar junction transistors. And so I've left the board from the last lecture as it is because we can work off of that. The first thing we need to do is we need to fill in our family of characteristics because as we discussed in the last lecture, out here in this active region where VCE is well above a volt, we can simply use the relationship IC equals beta IB to draw our family of characteristics. And beta is given by this formula where alpha is the base transport factor, so it's close to 1. And R is the ratio of the base emitter hole current, or in current we don't want, to the electron current. And so we want R to go to 0. And so as we discussed, as alpha goes to 1 and R goes to 0, beta goes to infinity, which is our desired result. All right, well that's all in the active region. And we just have to complete our picture here, which isn't very hard. You'll see it's very easy to do, of what happens as VCE gets smaller. Now, we sort of started that discussion last time. VCE is this voltage here, and VBE remains fixed because it is fixed by the input to the transistor. The base emitter transistor junction remains forward biased, and so as you know, to a forward biased diode, you need a voltage of around 0.7 volts. And so what happens is that because if you look at the diagram, if you look at the schematic, right, you can see here that VCE, right, the voltage of the collector to the emitter, that voltage, is the sum of these two voltages, right? Minus plus, minus plus. And if you look at how we've drawn them, of course VBE is always positive for forward bias because we're doing NPN, and so that's the voltage of the P base to the N emitter. And remember your mnemonic: forward bias, positive P side. While for the active region, we want the voltage of the collector to be positive with respect to the base, and since we put a positive bias on the N collector, it reverse biases that junction, which is our desirability to suck all those electrons flying over the base into the collector. All right, so this is pretty easy to see, and so we can just rearrange that to VCB is equal to VCE minus VBE. And so, and we want that to be greater than 0 for what we call active operation. All right, and since VBE is 0.7 volts, as long as we're well above a volt, you'll see it's even less, we're good. And this junction remains reverse biased. All right, so to complete the picture, we have to just essentially draw what happens when VCE gets low enough, right? Now, you can sort of see when VCE is equal to VBE over 0.7 volts, then the base collector junction is not biased at all. It's 0. And then when VCE drops below that, it becomes forward biased. Okay, so we've kept our injected carrier distribution diagram here, and I'm going to erase this. This curve was just sort of to start the presentation, but remember, this is what's going on in the active region. The injected electron density in the base is approximately a straight line with our formula for the injected density at the junction, and going down to 0 at the base collector junction, because that acts like our vacuum cleaner. Okay, so now what happens as VCE gets as VCE becomes negative, and which means that this becomes forward biased. Well, it becomes a forward biased junction, and you know what that does. Okay, and I'll just draw it here. It becomes that. Because now, okay, so this, I should have kept that there. I apologize that everything's getting, and I'm trying to figure out where to put this. So that's for VCB is greater than 0, which is our reverse bias condition. Let's see if I can draw that bigger. All right, that's our active region. And then what happens is that this curve is for VCB is less than 0. Because when it's less than 0, then it's a forward bias junction, and now we have now basically we have sort of counter operating junctions, forward biased. Now the forward biased base collector junction is trying to emit electrons that way. And I don't want to complicate this diagram because I don't want you to, there's no reason to. All we got to do is realize that now this point is NV0 times e to the e v. Now we got to be careful with our designations here, because remember, to get this value we have to put the forward bias value there, and so that's actually now VBC over KT, which basically means as VBC, the voltage of the base with respect to the collector, becomes positive, that then lifts this up, okay, and it has, you know, some non-zero value. So this is the active region over here, and then this is what happens when you start to get close to small collector emitter voltages. All right, so I mean, you know what to do now, because all you have to do is now use this straight line to calculate JEN. So JEN now is equal to, okay, E VE times this slope, and that slope is basically NV0 e to the E VBE minus that value, NV0 e to the V BC over KT over XB. All right, so we can bring the common terms out. I'm going to try and fit this in here, so bear with me. Okay, so I just brought out the NV0, and now what I'm going to do is I'm going to write this as e to the E VBE over KT. All right, minus, all right, and now what I'm going to do, draw this a little better. Okay, what I'm going to do is I'm going to use the relationship that I erased. Okay, and I'm just going to have to draw it. So basically, VBC. All right, now we have to flip that. Okay, let's do it over here. Okay, so now VCE. All right, let's do it up completely. We have a little space over here where we can do it, because I don't want this to be confusing at all. Okay, let's rewrite our relationship. Okay, and that's easy. You know, I always find it easy to do Kirchhoff's law when everything, you know, sort of fits together. Minus the plus, so that equals that plus that. All right, and you just have to realize that when I reverse the letters here, because then now I want in this formula, I want the voltage of the base with respect to collector. I just put a minus sign there. Okay, so now down here, I can substitute for VBC. Okay, VBC is equal to VBE minus VCE over KT. And you'll see in a minute why I did that way. Okay, so now I can see, I tried to plan this all out in terms of the available board space. So now I can write, try and do it very neatly. I forgot my bracket over here. JEN is equal to E DE NB0 over XB. And now I'm going to bring out E to the EVBE over KT times 1 minus E to the minus EVCE over KT. All right, and so I have to like put two steps together here because I got my last little quadrant of the board. But basically, JC is alpha JEN. So IC is then just this whole thing. Alpha, I gotta put A in there for area now. EDE NB0 E to the EVBE over KT over XB times 1 minus E to the negative EVCE over KT. But this term, this is, I mean, you don't have to like go back and do it. This is just, right, because remember when the slope was going to 0, it's just this term. So this is just, I'm going to write it as IC active. Times 1 minus E to the negative EVCE over KT. And so what you see is that, for example, if we're on this curve here, right, that's the active IC. And then it just gets multiplied times this term here, which basically, if you look at it, right, as VCE goes to 0, this goes to 0 because that becomes 0, and that's e to the 0, which is 1. 1 minus 1 is 0. And so it just looks like this. Oops. other curves do sort of the same thing. And you can see that this is not really right. It's really, like a few kT. Because you see, when BCE is bigger than a few kT, this goes away and it just becomes that. And in fact, since we know what IC active is, we can just write an overall formula. IC equal to beta IB times 1 minus e to the negative e to BCE over KT. And on an overall basis, that is our family of curves. So you see, when BCE is much bigger than KT, right, this goes away and it just becomes beta IB. And then when we get close, all right, when BCE becomes less than a few kT, then this starts to become greater than 0 and approaches 1. And at BCE equals 0, of course, it has to go through 0. Okay, so that completes our the description we're going to use in this course for bipolar junction transistor. IC is beta IB times that, where beta is given by this, alpha is the base transport factor, which I was thinking of a homework problem maybe to try and illustrate how you calculate the base transport factor, but we'll just leave it that it's something that you can determine. And R is the ratio of the hole to electron base emitter forward bias current, and is given by an analysis of these two straight lines. Okay, all right, so what I was going to do next is, just because, this isn't a circuits class, but sort of to tie everything together, perhaps from a circuit class, put this transistor in a little circuit and sort of figure out how to do it. Okay, and I think now, okay, so for purposes of the circuit we're going to draw, we don't have to worry about this region here, and so we're just going to use beta IB. So pretty much I can erase this whole side of the board for now, I think, and we can do our little circuit. So I'm going to erase this now. Okay, and so we're going to do the straightforward amplifier circuit, which is where we take our transistor and put it in series with put a bias here. Okay, so there's our little circuit, and we're going to label this V bias. Of course, it's positive. And this is V in, where V in is a little sinusoid, a little signal. And our out is going to be over here. And of course, the emitter is grounded. Okay, so you probably are familiar with this circuit. It's a common emitter. transistor amplifier circuit, and you know, you analyze it because V out is equal to VCC minus IC RL. VBE is equal to the bias plus Vn, right? That's VBE. Where Vn is small, right? It's you know, like, you know, the whole idea here is that this is just a little wiggle on top of V bias. So it's small. All right, and so all we got to do is we got to calculate what IC is, which you know how to do. It's written over here. IC, put in our area, times JEN times alpha, and so that's just, you know, remember, I mean, it's just this slope, right, to get our flux, and hence multiply times E to get our current in A. Okay, and so IC is equal to A alpha ED over XB. And now VBE is V bias plus Vn over KT. All right, and we can bring out e to the E by bias over KT, because then that's just IC bias, right? That's this term times E to the E Vn over KT. And now because Vn is small, now actually, you know, here's where, now you know, of course, you know what we're doing here. We're doing small signal analysis of a circuit. And you should be familiar with that from your other circuits courses. And, you know, interestingly, right, your other circuit courses never told you, well, how small is Vn? Well, now you know, okay? You know because it's small compared to KT. So it's much less than 0.026 volts. Okay, in which case we can write this as approximately 1 plus EVN over KT, which I hope I shouldn't have to tell everyone that, okay, remember how much I love the binomial approximation? Okay, same thing here. E to the x is approximately equal to 1 plus x. And if you need a refresher of why that's true, for the same reason that 1 plus x to the n is approximately 1 plus nx. Okay, you have to do, you know, the first order Taylor series expansion. But anyway, from that follows this here. And so we see that we have IC linearly in terms of Vn. And it's, you know, it's kind of done then. I mean, V out is equal to VCC minus ICRL So we just plug in VCC minus IC bias RL times 1 plus EVN over KT. And so we can kind of write that as V out bias, all right, minus IC bias RL E over KT VN. And this is our gain, our voltage gain. Which means that for a small signal in, we get that small signal out. And you can calculate, you could go through and you could calculate what this is. Clearly it's pretty large because, KT is small. It might be easier, if looking at this, to write it this way, KT over E. Remember, KT is energy, so at 300 Kelvin, it's 0.026 volts, okay, and KT over E is volts, and so, if you're using KT in electron volts, KT over E is volts, the same number, 0.026 volts. And so, however you set your bias, this gain can be quite high, and however you set RL. All right, and okay, I'm just going to make one. Let's see where I put it here. V out is V out bias. And now I'm just going to plug in for, remember we're working in the active region, so I'm just going to plug in beta IB bias RL over KT over E VN. So what we've done here is we've done what you did in some course, some circuits course, which is we did what's called a small signal analysis of this circuit. And you remember from your circuits course that when you do a small signal analysis, it's from a small signal model, okay, which we didn't employ here. We simply employed our knowledge of how the transistor works to come up with this formula. Now, if you go back to your circuits course, all right, what you would have done with that is you would have rendered it in a small signal model. See, this looks familiar too. All right, and this is now Vn, our small signal voltage. And remember this, what you called this R sub B in quotes, right? And R sub B was something that they made up for you. So if you do it that way, right, you get that IB, and now we're going to start using little letters, remember? IB, the small signal current, base current, is Vn over RB And so we would have written that V out, this is still RL, is equal to VCC minus IC. And IC, I'm just going to skip steps, is beta IB RL. And what is IB? IB is, in the small signal model, Vn over Rb. And so we basically have RL over Rb Vn. And I gotta use little letters. and we would have analyzed it that way, and that would have been the gain from some unknown Rb. All right. And you can see up here, well, where is it? Over here, that in fact Rb is equal to IB bias over KT over E. So now you know how to figure out what Rb is actually. And okay, so how do we figure this out? Well, we plot IB versus VBE. Now, in our whole analysis, what I told you was, the way I taught this was, remember, we never worried about JB. I was like, JB takes care of itself. We have to know what JE is, we have to know what JC is, and then we just use the relationship that JB plus JC is JE. And so we never, okay, now here's where we actually have to think about what IB is a little bit. Now, the thing is that IB is related to all these current components, all right? But every single one of them goes as, oops, oh, where is it? Goes as e to the EVB over KT. We're in active, so that goes away, all right? So IB versus VBE is going to be some IB naught, just making up something, times e to the EVB over KT. Now, let's see if I can draw that a little bit better. So it has a continuously varying curvature. Kind of. All right. So what we do is we bias IB, whoops, this one, IB bias. All right. So that's set by our bias voltage up there at some value over here. And then remember, in small signal, what matters is delta IV over IVCB. And so it's this slope. The slope is 1 over RB. But what's the slope? Take the derivative of an exponential. Okay, so delta IB over delta VBE, that's 1 over RB, right? Remember, R is volts over current, so current over, it's 1 over. All right, and I ran out of room, so I'm going to have to just scrunch this in here. But you know how to take the derivative of an exponent, right? You just bring out an e over KT. So this is just equal to I bias over KT over E, taking the derivative. And it's exactly what we got there. So you see, either way, understanding, okay, that this goes as a diode current, we can get that R sub B is this, that slope, or we can just use our direct knowledge of how to calculate things to come up with the same thing. Now at this point, I should issue a disclaimer. The disclaimer is that, okay, so what I basically showed you is that this RB in your small signal analysis is just equal to IB bias over KT over E. And it just comes from the fact that it's the slope of the diode curve. But in real life, the transistor is not perfect. The equations are not ideal, and the transistor may have an input resistance that dominates over the diode resistance. And so don't use this, is what I'm saying. The reality is that the guys back in the circuits course in 309 were right to just call this some RB, because for a non-ideal transistor, there's going to be circuit resistances and things like our input resistances, and so you should just kind of, and the reality is, measure what RB is by looking at the actual characteristics of the transistor. Okay, but I wanted to do that to sort of try and tie it in a little bit with your use of the device in a circuit. Now, the last thing we're going to do is we're going to make a better bipolar junction transistor. We can actually sort of maybe tie things in a little bit here. I'm going to erase our circuit. I'll erase this part. And we'll just keep our small signal model with our RB there. All right, now let's draw, I've done this once before, but let's draw the actual transistor, what it looks like. So basically you have an N substrate, that's our collector, and you make a P diffusion, and then you make an N diffusion. Okay, N, P, N, and that's our bipolar junction transistor. And this is our emitter. And so let's actually draw context. So there's our emitter contact. And the base contact, basically, what I'm drawing here in cross section is actually a ring. Typically, if you drew this three-dimensionally, it would look like a circle from the top, and so the emitter contact is here, and then the base contact is kind of the donut going around it. So kind of like that, and then we could put a contact in the back of our substrate, and that would be the collector. All right, so I lift this up because, as I said, okay, when you, if you have an ideal transistor, right, it's this slope which can be very high, which means RB can be very, very low. All right, and then our gain can be very, very high in the circuit. And the problem with that is that the way we've designed our transistor, remember, we want the base doping to be much, much less than the emitter doping. And additionally, remember, this is XE, and XB is our base thickness. Remember, that picture is this turned on its side, so XB is that thickness there, and we want XB to be much smaller than XE. All right, and if both of those things are true, then this slope is much higher than that slope, and this is much bigger than that. And all sounds good, except that both of these conditions lead to high base series resistance. Which we have neglected in the picture, but basically there's a large series resistance if you think about it. Okay, that basically that base current has to flow this way, and it has to flow through this sort of narrow channel here. And because the doping of that channel is very low and the thickness is very thin, that leads to that RB, or I'll put R series, too high, which leads to RB too high, which leads to low gain. Now, we haven't performed high frequency analysis, and we might circle back and do that. But if you remember your circuits, if you have high resistance, your high speed time constant is very, your high speed characteristics suffer as well. So for both reasons, RB, R series being high and hence RB being high, well, that's not good. Okay, now we did this to get high beta. So the two are working against each other. We did this to get high beta, but we're also getting high RB. And so, one's on the numerator, one's on the denominator, and it's not working out. So a very smart person who was my professor a long time ago came up with a solution to this problem, because he noted that, and unfortunately I'm using the same letter, but remember this ratio of JEP to JEN, right, is given here. And I'm going to start here. Okay, that ratio is DH XB times PE0, which is NI squared over NE, DE XE times NI squared over N base, right? All right, NI squared over N base is the equilibrium minority concentration in the base, and NI squared over NE is the equilibrium minority concentration in the emitter. Now, we went to the next step there because the NI squared canceled out, right? Well, they don't have to. Because if you make, remember, okay, so I'm just going to keep writing here. It's the easiest way to just show it. DH XB DE XE, put the NE down there, and put the NB up there. So that's what we had before, but now I'm going to keep NI squared. And the reason I'm going to keep it is that I'm going to write this as NI squared emitter and NI squared base. Wow, okay, so that looks a little weird, except for the fact that, okay, what I'm doing here is I'm going to make the band gap of the emitter much larger than the band gap of the base. And when we do that, we call that a heterojunction. Bipolar transistor, or an HBT, which you may have heard about in some of your circuit dealings or otherwise. It's called a heterojunction because the word hetero comes from dissimilar. So we make a junction from dissimilar materials. Now, how do you do that? Well, there's various ways of doing it. This isn't a course in fabrication, but one way would be to, well, actually, kind of the only way to do it is to fabricate our transistor differently and not use diffusions, which is, okay, this, okay, I'll just write out what the typical materials are. So you make N silicon, and then you grow by epitaxy P silicon germanium. And then you grow on top of it and silicon again. And the band gap of silicon is greater than the band gap of silicon germanium. So you basically make it by epitaxy instead of diffusion so that you can have dissimilar materials here. And silicon germanium, okay, there's other materials you can use. I mean, these are what's called group 4 materials. And the advantage of making it using group 4 materials is that this can then be integrated with CMOS. And so what's called bi-CMOS is equal to CMOS plus HBT based on silicon germanium. And it can be fabricated in the same way for that. You can also do this by fabricating like 3,5 materials. Like this could be gallium arsenide, and this could be aluminum gallium arsenide, or various other ways. And anyone is especially interested in this is called band gap engineering. You can talk to me offline. But what it does is it changes those NIs, because NI, remember, NI squared is NC, NV. Remember our friend, right? This is our our most wonderful friend in the world that we know we can calculate N and P from NC in the gap and stuff. All right, E to the negative E gap over KT. Now here, what I'm going to do is I'm going to just sort of approximate. It's not really true because the effective masses change a little when you change the material, but we'll just sort of pretend that NC and NV, the effective density states, are the same for the two materials. So we're really going to write this R as DH XB NV, and now NI squared is e to the minus E gap emitter over KT DE XE NE e to the negative E gap base over KT. By the way, my old professor won the Nobel Prize for this. Since the band gap of the emitter is higher than the band gap of the base, this ratio here can be very, very high because it's e to the minus a bigger number over a smaller number. So this allows me to up the doping of my base or even the thickness if I want to, without compromising beta. Remember, beta is alpha over 1 minus R minus alpha. So now I can make this very, very small by making the ratio of E gap E of the emitter. Uh, and because it goes as an exponent and an I squared, you don't have to have that much different band gaps to get a huge effect from these terms here. So now it allows me to make my base doping high again, and I just have to have a larger band gap in the emitter, and I can still make R very small and get a large beta. So it solves the sort of fundamental conundrum of how to get high beta and low RB at the same time. And there's a lot more we could talk about in terms of HBTs and stuff like that. You know, BiCMOS has enabled a wide range of circuit technologies because you can have essentially high gain transistors for analog type circuits and things like that on the same substrate as CMOS, you know, digital transistors, and they all can all be integrated into the same substrate. All right, so that completes our discussion of bipolar junction transistors and the variant heterojunction bipolar transistors. You know, so when you see the letters HBT, you know what that's talking about now. The next lecture for Wednesday, we're just going to go over the homework I assigned. Homework, I think it's 7. And next week, we'll get started on MOSFETs. Okay, so that's it for today.